All right, good morning. So today we're going to talk about 14.8, the Jacobian Transformation. Let me zoom in on that a little bit. Okay, so basically what we're doing is we're saying a lot of times our region that we want to integrate over is not real conducive. It's not real easy to integrate. Okay, so if we have a double integral of, let's say, f of xy dy dx, okay, this thing is your dA. Okay, but sometimes dx dy or dy dx, sometimes this thing is not going to be real conducive and real easy to integrate. So we can transform this and we can say, well, x is some function of u and v, or like in polar coordinates, a function of r and theta. Y is some function h of u and v. Okay, we'll use u and v just to be generic. It could be any kind of transformation. Okay. And so your f of this x is now your function. X is g of uv, and your y is h of uv. Okay, and what happens to this thing, your dA now becomes a du dv, but you need this Jacobian matrix in here, which we abbreviate as d of xy over d of uv. Okay, where this thing, d of xy over d of uv, okay, and it's assumed that these functions g and h both have continuous partial derivatives with respect to u and v. That's going to be important when we draw the region, make some assumptions about this. Okay, so this thing is really just the dx du partial, dx dv partial, and then dy du partial, and the dy dv partial. Okay, and that's the thing, this determinant, the magnitude of this thing, is what gets thrown in here as this dA transform into this new dA. Okay, so normally we do a transformation because on the UV plane we want something to be a rectangle. So we'll call this region S. Okay, there's your region S. And this point right here is going to be U comma V. And this is really just a tiny, tiny little area that's part of your region. Okay, so then as we move in the direction of U, now we're going to add a tiny bit to the U. So now this point is going to be U plus delta U, comma V. Notice the V didn't change. We didn't go up or down. This point right here, now the V changes and the U doesn't change. So that becomes U comma V plus delta V. Delta V, sorry. And then this point right here, both of them have changed. That's U plus delta U, comma, V plus delta V. Okay? And when we do this transformation, now this thing is on the XY plane. Really, you've transformed usually from this to this, but we can look at it either way. This one's a nice rectangle because we want it to transform into something really nice. But you've got a point here. Let's call this M. And this is really your xy. This is g of uv, comma, h of uv. Okay, remember what that is. Your g of uv is just your x. Your h of uv is just your y, the way we define those up here. Okay, now when we want to map this point onto this region over here, now we're adding a tiny bit to the delta u. So this point right here is going to be, we'll call this point N. This is going to be x of, but now u of delta u, x of u plus delta u, comma, v, comma, and then the y of u plus delta u, comma, v. Okay, so we're plugging in this point to both these two functions. Okay, now we're going to do the same thing, but over here. This is going to go to a point, let's call this point Q. And now we're plugging this point into the G and the H functions, your X and your Y values. So this is going to be G of U, comma, V plus delta V, comma, H of U, comma, V plus delta V. Okay, and that's your point Q. And then we've got this point over here, which is going to be your point P, okay, which is going to be plugging in this point. So that's going to be G of U plus delta U, comma, V plus delta V, comma, H of U plus delta U, comma, V plus delta V. Okay, and this is our new region R. Okay, now we're assuming this delta U and this delta V, they're ultimately going to be infinitely small. They're going to become a du and a dv. But right now, for our purposes, we're thinking of them actually having a really small value. Okay, and these, remember, these partial derivatives exist. And we want to know what these partial derivatives are, because this is going to come in handy later. The dx du. Okay, and remember, x is your g function. So this you can think of as gu of u, comma, v. Okay, and remember what the definition of a derivative is. It's the limit as your delta u, taking derivative with respect to u, goes to 0 of, okay, g of u plus delta u, comma, v minus g of uv over delta u. Okay, and then we've also got, and we can think of it, I'm going to do one more step, and that's as delta u goes to 0, but we're going to think of this before it goes to 0. We're going to think about it as a tiny approximation. So before we do this limit, we could really say that this thing is roughly equal to the g of u plus delta u, comma, v minus g of uv is roughly equal to this thing times your delta u. So gu of u, comma, v delta u. Okay, so we're going to come back to that in a minute. But now we're going to do the same thing here with the dy du. Okay, which is your hu of uv. Okay, that's the u partial derivative of h. Remember, h is your y value. Okay, and that's going to be equal to the limit as delta v goes to 0 of h of u plus I'm sorry, I don't want delta v going to 0. It's still a u partial derivative. Delta u going to 0. So that's going to be h of u plus delta u. Remember, we're still adding this to the x coordinate. But this is our y value. So this is how we calculate the g function is how we calculate the x value. The h function is how we calculate the y value. Okay, so dot v, comma, v minus h of uv over delta u. Okay, so now we can do the same thing. If we take this and multiply by this, we have hu of uv delta u, okay, is roughly equal to this thing, h of u plus delta u, comma, v minus h of uv. Okay, you will see, I promise, soon we'll see where all this is going. Okay, so these are our partial derivatives. We know that these are defined, so therefore, no matter what shape this is, since the partial derivatives with respect to u and v are both continuous, that means that this thing should look linear if we zoom in enough. If the delta u and the delta v are small enough, as we zoom in, this is going to look linear, and we can approximate it by this thing, which is a parallelogram, which is convenient because we do need to know that this delta A, so this delta A, this dA, is equal to the magnitude of mn crossed with mq. Okay, so this delta A is going to be equal to this thing. Okay, now let's move on to the next thing I want to talk about. I'm actually going to do this on another page because we're going to be referring back to this. So now I'm going to define mn and MQ. Okay, so MN from up here, MN, this vector is equal to just final minus initial. Okay, so it's the vector G of I should have called these G and H instead of X and Y. They're the same thing. It's still X and Y, but I'm going to call them G and H just to be consistent. Okay, so this is going to be G of U plus delta U comma V minus G of U comma V. And then I've got this one, H of U plus delta U comma V minus H of UV. Okay, so there's your MN. Okay. And then let's do the MQ. I'm going to leave some space here because we're going to do something in between. The MQ is equal to, so this is M and this is Q, so we want final minus initial. So that's going to be G of U comma V plus delta V minus G of UV comma H of U comma V plus delta V minus H of UV. Okay. Now, we're going to go back to the other page where I did this. Look at how I defined this here. This thing right here, well, what do you know? That's the same thing as this right here. So I'm going to replace this thing with this. This is now GU, the U partial of G at U comma V, delta U. And the second part, because this was our Y value, I'm going to replace this thing, which is the same as this thing. I'm going to replace this with this, H of HU, the U partial of H at U comma V, delta U. Okay, and that's your MN. Okay. Now, I could do the same thing. See how I did dx du and dy du? I could do the same thing for dx dv and dy dv. I'm not going to go through all those steps, but you could do the same exact thing. And then this here, this one is going to become the gv, the v partial of u comma v, delta v. This is mq. And then the v partial of h of uv, delta v. Okay, so now I've got my mn and I've got my mq. I promise you we're almost there. So now we're going to do this cross product. Okay, remember I said this thing, the dA, the delta A, and when this delta becomes infinitely small, that becomes a dA, is going to become the magnitude of this thing. And we're going to show how this thing, this delta A, turns into this. So we're almost there. We're showing how this becomes this through this and through how we define Mn and Mq. Okay, so our delta A is equal to the magnitude of this thing crossed with this thing. So Mn crossed with Mq. So let's do that cross product. I, J, K. Okay, so I've got a GU of UV, delta U, and I've got a HU of UV, delta U, and that's 0. Okay, now I've got this one, I've got a GV of U comma V, delta V, and I've got a HV of U comma V, delta V, and a 0. Okay, another way to write this, because remember what this is. G is your x function. G of uv is really just your x value as a function of u and v. So I'm going to rewrite this as I, j, k. This is just dx du. And there's your du. I'll still call it delta u. Okay, I'll just call it a delta u until the very end. Okay, and this is your y value. So this is a dy du delta u, and that's a 0. And this thing is a g is your x function, so that's a dx dv delta v, and this is a dy dv delta v, and that's a 0. Okay, now doing this cross product, we're going to get the I times this minus this, which is 0, minus j times this minus this, which is 0. So we get a 0, comma, 0, comma. In the k direction, we get this and this. So we get a dx du times a dy dv delta u delta v minus, and then we get this thing, dx dv dy du times your delta u delta v. Okay, and we want the magnitude of this thing, which is simply going to be the magnitude of this. Okay, we can factor out that delta u delta v, and what's left with is the magnitude of dx du dy dv minus dx dv dy du, and then you factored out the delta u delta v. Okay, starting to look familiar. This thing right here is your Jacobian. That's just your dx du dx dv dy du dy dv, and as these become infinitely small, that's just your du dv. Okay, so this is your new dA. Okay, so we basically just showed that this thing on our first page, okay, that's where this comes from. That's where this dA, the dx dy, turns into this thing, and that'll work for any transformation as long as you define x and y in terms of u and v, any two other variables, any two other parameters, okay, and as long as these have continuous partial derivatives with respect to u and v, okay, and that's it, and that's how and why the Jacobian works.